in the cold, dark reaches of interstellar space, far from the warmth of any star and invisible to human eyes. The universe is quietly at work, assembling the ingredients of galaxies, stars, and planets. These vast regions, often cloaked in darkness and silence, are called star nurseries or stellar nurseries. They are immense clouds of cold gas and dust, stretching across hundreds of light years, harboring the raw materials that will one day ignite into blazing suns and coalesce into orbiting worlds. It's in these regions that the process of stellar and planetary creation begins, slowly, chaotically, and with stunning complexity. Star nurseries are not places of peace. They are turbulent, volatile environments, shaped by the gravitational pull of gas and dust, the shock waves of supernovae, and the energy radiated by nearby stars. Yet within their violent interiors, something miraculous happens. Gravity works its quiet magic, pulling together clumps of matter that will one day shine as stars and eventually give birth to planets, moons, and perhaps life itself. To understand where planets come from, and ultimately where we come from, we must journey into these distant cosmic wombs, where the story of every solar system begins. Star nurseries, scientifically known as giant molecular clouds, are enormous concentrations of cold interstellar gas, primarily molecular hydrogen, mixed with fine dust particles. They can contain the mass of thousands of suns, spread across vast regions of space. At first glance, or through a visible light telescope, these clouds appear as empty voids or dark patches against the backdrop of stars. But in reality, they're densely packed with potential. It's only in infrared or radio wavelengths that we begin to see their true structure. Filamentary networks of gas stretching like veins through the galaxy. Famous stellar nurseries like the Orion Nebula, located about 1,300 light-years from Earth, offer a rare glimpse into this hidden process. Within its glowing cloud, hundreds of young stars are forming simultaneously, each surrounded by its own disk of dust and gas. These nurseries serve as cosmic factories, continuously recycling the remnants of past stars into the next generation of celestial objects. Over tens of millions of years, these clouds birth entire clusters of stars, some of which will go on to form solar systems and possibly harbor life. But how do these immense clouds, scattered across light years, begin to collapse into the dense, bright objects we know as stars? The first step in the birth of a star, and eventually a planetary system, is collapse. But a molecular cloud doesn't simply fall inward on its own. It needs a trigger, a catalyst that nudges the balance between internal pressure and gravitational pull. This trigger might come in many forms. A nearby supernova explosion can send shock waves through a cloud, compressing regions until gravity takes over. Or the intense radiation from massive, nearby stars can heat and sculpt the edges of a cloud, creating dense pockets that begin to shrink. As the gas collapses, it forms dense clumps called prestellar cores. Over time, these cores become smaller and hotter, spinning faster as they contract. Conservation of angular momentum causes the core to flatten into a rotating disk, the early version of what will become a solar system. At the center of this spinning system is the protostar, a newborn star that is not yet fully formed. It's still gathering material from the surrounding disk, heating up under the pressure of gravity, but not yet fusing hydrogen in its core. Around it, dust and gas swirl like water down a cosmic drain, setting the stage for the next phase of creation, the formation of planets. While the protostar grows brighter and hotter, the material in the surrounding protoplanetary disk begins to evolve. This disk, rich in metals, silicates, ices, and organic molecules, becomes the birthplace of planets. Tiny dust grains, suspended in the gas, begin to stick together through electrostatic forces. These microscopic particles form millimeter-sized clumps. Over time, through countless collisions and mergers, these clumps become larger, forming pebbles, rocks, and eventually planetesimals, which are asteroid-sized objects. These planetesimals crash together in a chaotic process called accretion, merging into larger bodies, some as large as Mars or the Moon. In the colder, outer regions of the disk, ices allow these bodies to grow even larger, capturing vast amounts of gas to form gas giants like Jupiter and Saturn. Closer to the star, where temperatures are too high for ices to survive, rocky worlds like Earth, Venus, and Mercury take shape. But this process is far from smooth. Entire planetary embryos may be destroyed in violent collisions. Some are thrown into the star. Others are flung into deep space, becoming rogue planets, adrift in the galaxy without a sun. What remains after millions of years of gravitational chaos is a newborn planetary system, each world orbiting its star, locked into a complex and delicate dance. For most of human history, we could only imagine how stars and planets formed. These processes took place over millions of years and across unimaginable distances, hidden behind veils of dust. But in the last 2 decades, technology has changed everything. Modern observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile and the James Webb Space Telescope, JWST, in space have given us unprecedented access to these hidden regions. Using infrared and millimeter wave light, they can peer through dense dust clouds and directly observe protoplanetary disks in exquisite detail. We've now seen disks around young stars with rings and gaps, signatures of forming planets sweeping through the dust. We've detected jets of gas blasting out from protostars, clearing paths through their clouds. We've even captured time-lapse images of evolving disks, watching the very first stages of planetary system formation in real time. These images are more than just scientific data. They are windows into the past, glimpses of the same processes that shaped our own solar system over 4.5 billion years ago. What makes star nurseries truly profound is not just that they create stars and planets, but that they may also sow the seeds of life. In the cold, dark environments of molecular clouds and protoplanetary disks, scientists have detected a remarkable variety of organic molecules, including amino acids, sugars, and precursors to DNA. These complex compounds are thought to form on the surfaces of dust grains or within icy mantles in the coldest parts of the clouds. If planets form with these building blocks already in place, it raises a tantalizing possibility that life's essential chemistry might be present from the very beginning, woven into the very fabric of a planet's formation. This idea has profound implications for the search for life beyond Earth. It suggests that life may not be a rare fluke, but a natural outcome of planetary formation, one that could be playing out in countless star systems across the galaxy. Every star nursery, then, is not just a forge for stars and planets. It may be a cosmic incubator for biology. Inside the hearts of star nurseries, matter becomes energy, dust becomes planets, chaos becomes structure, and silence becomes light. These colossal clouds, scattered throughout our galaxy, are the starting points of every story ever told. Our sun was born in one of these nurseries. So were all the planets in our solar system, and so were we. By studying these distant clouds, we are learning not just about physics and astronomy, but about ourselves, where we came from, how we got here, and whether we might share this universe with others. In the swirling chaos of a star nursery, we find the ultimate paradox that in the coldest, darkest corners of space, the forces of nature are quietly building the seeds of warmth, light, and life. The universe is still forming stars, still building planets, and somewhere out there, in a glowing pocket of interstellar gas, another Earth may be waiting to form, waiting for its own story to begin.